figure out how to kind of order it.
Well, welcome again to the Fall 215 Math Staff Department Colloquium Series. Today we are fortunate enough to have our own Professor Michael Robinson giving a presentation. And I'd also like to direct you to a rather spectacular set of lectures that Professor Robinson gave this summer. Exactly when was that?
End of August.
End of August. I've looked at them and I find that not only are they excellent lectures, but I'm really impressed with his stamina. The fact that he could lecture for 2 days straight. I want to know at the end of this, did he just go home and sleep, collapse, or wrestle with his boys? I think he probably did a little of all of these things. So. Yes. Today's lecture is something I requested, and I'm really happy that he came through it. So he's going to teach us a wonderful computational tool that he uses in his research, and this is computation of the Godement resolution for sheaves over finite spaces. With that, Professor Robinson, thank you.
Thank you, Steve, for inviting me, and thank you for all of you being here, and thank you to the students who have requested for this to be recorded so they can watch it while they're taking their class, so it's going to go online afterwards, so thank you to your suggestions as well. So I want to
press the on button.
I think the on button has been pressed. Yes,
it's blinking in it.
It's blinking, excellent. So I do want to caution everyone, normally I give applied math talks. This is a math talk. You have been warned. So, cannot give a reasonable academic talk without thanking people who have helped to make it possible. So, of course, thank you to the sponsor, which happens to be DARPA. Thanks to some of my industry and government collaborators, as well as my students who have been discussing about this circle of ideas with me for some time now. So there they all are. Now, additionally, I want to say this is not new material that I'm presenting in some sense. What's new-ish about it is showing off that you can actually do these computations in a reasonable fashion. It's, in some sense, as old as the hills that one would want to compute sheaf cohomology. Well, there's lots of references. Here are a few, more or less in descending order of relevance. Most of this is based off of a PhD thesis of a friend of mine, Justin Curry. And then there was a much older PhD thesis that was written in 1985 by Alan Shepard, not the astronaut, talking about how to do computational sheaf theory in some fashion. And then, of course, some more venerable books as well. So the point of the matter is that we're interested in understanding sheaves over finite spaces. And the other good reference is the set of lectures that Dr. Casey mentioned, the tutorial on sheaves and applications that I gave at the end of this summer. These are lectures all online. You can go watch them on YouTube. There's about 8 hours of material. And there are also all the slides up there as well as some exercises. So avail yourself of these if you're interested. Okay, so I'm going to talk about sheaves over finite spaces. Most of the spaces that people tend to work with in topology are not finite. Like the real line, for instance, is pretty not finite. So I'm interested in spaces that are finite. Why? Well, because you can compute with them. You can actually write down sheaf cohomology over finite spaces because they're finite. You can actually literally write it down. So I want to know what a finite space is, and it's a topology. Now, topological spaces, there's a lot of them out there. This is sort of a partial taxonomy. There are lots of topological spaces. There's the standard topological space. There are manifolds. Manifolds are kind of nice. They look like Euclidean space. And then there are many different kinds of other things that are built off of bits and pieces of manifolds, and more complicated objects that have more and more structure as you move up in the diagram. On the other hand, on this side is topology, on this side is combinatorics, which feels very computational. In this sort of blue region, these are structures that are combinatorial but feel very topological. So things like an abstract simplicial complex, which we'll see in a bit what they are. They really feel like you ought to turn them into a topological space, and indeed you can. On the other hand, if you remove some of that structure, you get things that are very basic, things like preorders. They too have an instantiation as a topological space, and in fact topological spaces can be instantiated the other way as preorders. And so there are lots of interesting topological spaces out there. The ones we're interested in this talk are here, so the pre-orders, finite topological spaces, and abstract simplicial complexes. That's where a lot of very computationally tractable, again I said this is not an applied talk, but sort of influenced by applied, these are computationally tractable spaces. And the sheaves you build over them are computationally tractable. Okay, so those are the topological spaces out there. Let me remind you what I mean by topology, because it really comes to the fore when we're talking about a finite topological space. So what's a topology? Well, I start out with a set, and I build a collection of subsets. That collection of subsets is a topology when, well, it's got the empty set, it's got the whole set. I can take any unions I like, and I can take finite intersections, and it's closed under each of those various operations. Those sets are the open sets for the topology, and if you pair them up, you get a topological space. And we just saw a partial taxonomy of topological spaces. There's a lot of them. Okay, now I'm really interested in finite topological spaces. Those that are built up in some way from a finite set X. Now, just outright finite topological spaces it's like a huge topic in some sense. It's a topic people haven't really studied very much. There's some notes a few years back by Peter May that looks at finite topological spaces from a purely start from the axioms and see what you get. How many different types of topological spaces are there? That's actually a meaningful question when you're talking about finiteness, because I can actually count them. It's actually computationally really hard when you get more than about 5 or 6 points, if you want to enumerate all the topologies of different types. So I want to put some constraints so I can actually talk about this. I want to talk about pre-orders. Those are sets that have some kind of ordering relation on them, which is to say this set, this point comes kind of before this point, which comes before those points. It's transitive, it's reflexive, but it's not necessarily transitive reflexive, but it's not necessarily the anti-symmetric, which is to say that I can have a point that comes before another point which comes before the same point. You can have these directed loops in a pre-order. If this were a partial order, that's not allowed. So pre-orders permit this sort of thing, and it doesn't cause any problems in what I'm doing, so I might as well just use a pre-order. Now how do I give a topology on this sort of thing? Well, you look at all the sets of the upsets, the sets of things that come after. So for instance, if you look at all the things that come after this particular element, well, this one came after, so did that one by transitivity, came after it, as did this one, as did this pair as well. So that, I'm going to think of that as an element of my topology. Think of that as an open set. Well, there are other ones. Say I could take the union of these things to make other ones, like a union of these two. So here's, this one doesn't have anything that comes after it. And if I take this guy over here, I automatically pick up the one that it's looped in with and all the rest. So these are, the unions of these sorts of things form my open sets. Of course, any good student of topology knows that I can get closed sets by taking the complement of open sets. So like, that's a closed set. Cool, okay. The other thing that I should be able to do is I should be able to intersect these things. If I intersect them, they better be closed under intersection. See if that works. Well, here's two of them. Here's the upset of this guy. Oops. The upset of this guy and the upset of this guy. If I intersect them, they're the upset of that guy. All right, that seems to work. And, this works if I take more of them. So like I add another set, take a look at the upset of this guy as well. The intersection is then the upset of that. And again, I might have to put in unions of these guys to make it work, but it's closed under intersection as it should be. And of course, it's closed under union because I asked it to be closed under union. I said it's the unions of all of these guys. So that's a topology. Now, it's a topology over a finite space. And I said that topologies have to be closed under any unions and finite intersections. Well, gosh, I only have finite intersections to check. So in fact, a space in which I'm allowed to take any intersections that I might want to construct is called an Alexandrov space. Well, therefore, easy proposition, practically doesn't even deserve the name proposition, is that all topological spaces over finite sets are Alexandrov. Now, in topological spaces, generally speaking, there are these things that are called closures. All good students of topology know that you can compute closures of sets. Maybe they're hard to compute, but nevertheless, you can compute them. On the other hand, if you have an Alexandrov space, there's an open analog. These guys are closed, there's an open analog called a star. You can't, in general, compute stars, but in Alexandrov spaces, you can. So what's that? Well, first, let's think what is a closure. If I take a set A, just this single point right here, and ask for a closure, that's the smallest closed set containing M. Smallest closed set containing A. Well, that's going to be complicated of an open set. So let's see here. If I took a look at an open set that I could make as big as possible to not contain A, well, I can pick that one, and like something over here. And if I pick this one here, it's going to contain A. I want the complement to contain A to make it a closure. So I've got to pick this guy, and then that drags in this loop here. Of course, because this point is in here, I've got to get that guy in there as well. So this is the closure of this set A in this topological space. And regardless of topological space, I can always form closures. But I can't necessarily form the analogous concept for open sets. Find me the smallest open set containing A. Can't do that in general. For instance, let's take the real line with the usual topology. Take a single point. Ask me, what's the smallest open set that contains that single point? Well, you can keep shrinking and shrinking and shrinking, and keep getting smaller and smaller and smaller, but you'll never actually get an open set that is just that point. It's not in the topology. On the other hand, in an Alexandrov topology, that concept is actually well defined. So in fact, here is the smallest open set containing A. In fact, it's just the upset from A. So Alexandrov topologies always have these stars, and they turn out to be really useful. Because in particular, if you want to think about information that's localized to a particular point, you want to localize it to the star. In a general topological space, you can't do this, and you have to do a limiting construction. Here we don't have to do a limiting construction, it just happens. We're good to go. Okay. Now, this is finite topologies on a pre-order. There are some even constraints that I can put on the pre-order to make it easier to understand what it is. And that's through the construction of a simplicial complex. So what's that? Well, simplicial complex starts out with a collection of vertices, a bunch of elements of a set. And what I do is I start taking a look at pairs of vertices. If I take a look at pairs of vertices, that gives me a graph. All right, pairs of vertices are kind of nice. This is a structure that's very well used in data science. People love graphs. People have written out massive graph libraries. People are interested in massive graph analytics, where they talk about data structures that look like this topological space, and they've got billions of vertices, trillions of edges, or whatnot. They, of course, buy very big computers and use these things to justify buying those big computers. Not knocking big computers, they're pretty cool. But this is kind of just pairs. We could do better than that. We could throw in other tuples. Here's a tree. And we're back.
And we're back.
Sorry for that. You know what I think I'm going to do? I'm going to keep poking this thing every so often to keep it away.
Yes.
All right. Maybe the talk was too boring for the computer. Okay. Anyway, so if I take tuples, triples, for instance, then that gives me some additional structure I didn't have there. And I can make a choice about whether or not I want that triple there or not. So the only constraint now is that whenever I include one of these tuples, I need to include all of the subsequent subtuples as well. So if I have this triple...
Yes, so an observation has been made. You might want to be careful not to
Touch the wire.
touch the wire.
You
So,
And that's what did it. Okay,
Yes.
all right, excellent. We're
in
back?
theory, we're back.
We're back. Okay, so it looks like there's a wire I can't touch. Okay, so
This happens.
this happens a lot. Okay, so the point of the matter is, if I include this triple, I better include all of the subtuples, the doubles, the V1, V3, V2, V3, etc. Okay, so that's a simplicial complex. Now, simplicial complexes also have an analogous concept of star. Here's the star over V1. It's all the higher dimensional faces that are attached to that vertex. So there's two edges and this higher dimensional face. Okay, now what about if I take a look at the star over this other edge? Again, all the higher dimensional faces attached to that edge, just that one face. Of course, if I took the star over that triple, it would just be that triple. Now this term star here seems very much like the term star on an Alexandrov topology. Are they the same? In fact, they are. And really the point is, you can think of this simplicial complex as a partial order. It's a pre-order, of course, as a result, where I take each of the elements of my partial order, are the simplices, the sets in my simplicial complex, and I have it one before the other if one of those faces is a subface of the other. So I can turn my abstract simplicial complex into a partial order, and then think the stars in the Alexandrov topology of this thing are just the stars that I thought about over in the simplicial complex. So the word star means both the same thing in both contexts. Okay, cool. So that's very nice. Now, I need to tell you then, what is a sheaf? So a sheaf, as now my data friends like to tell me, I should think of a sheaf as a sheaf of something, a data type, on something, a topological space. So in particular, you can have sheaves of abelian groups over a simplicial complex. I could have a sheaf of, I don't know, a sheaf of sets over a manifold, or many, many, many other permutations are possible. I'm mostly interested in sheaves of vector spaces over what kind of topological space? These are finite topologies. Okay, so now I need to tell you, well, what is that thing? This is filling out the Mad Libs, but what is it? Well, here's the definition from more or less the standard book on the topic. So a sheaf on a topological space is contravariant functor, blah, 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 blah. Yeah. Sheaves assign data to open sets, which is to say, take an open set in your space. What a sheaf does is it gives you a data space on it. So, in particular, if I'm going to have a sheaf of vector spaces, it's going to take an open set and give you back a vector space. Give you a different open set, give you back a different vector space. Now, it doesn't do this completely willy-nilly. There's got to be some way to translate the information from one open set to the other. Okay, so how do we do that? Well, some kind of restriction maps, it's called. Now, this is the only applied slide in the talk. So, what is it? Well, over on the left side there, I've got the topological space, two open sets in a finite topology. The open sets are associated with two data sources, say cameras. And what do I do with those two cameras? Well, I take pictures with them. And when I take pictures, I get out images. Images are big honking vectors, vector space data. So what this camera number one does, it spits out an image, an element of that vector space. And camera number two also spits out an image. Now, the images probably don't exactly line up. They're not looking at exactly the same spot. And maybe, on the other hand, if the open sets are telling me that these are the regions in which the cameras are looking, then there should be some overlap if there is some overlap. And indeed, in these two pictures, you can see, well, maybe you can't see very well, but they look like they're more or less the same scene. In fact, they really are. Basically, this part of the image on this guy is kind of over there in some fashion. So if I want to take these pictures and kind of understand what's going on, here's what a sheaf does. A sheaf takes those two open sets, takes a look at the intersection, and summarizes what happens in the intersection. So it takes an image here and finds it's either sub-image or some other descriptions, maybe some other vector space description of what's going on here. If I'm thinking very applied, it's going to give me a list of what the objects are in some fashion. Run a machine vision algorithm on it to say, I see a cup and a bowl and a spoon in the intersection. And similarly over here, I see a cup and a bowl and a spoon. Well, if I've got all that information, that object there, thus far, is a pre-sheaf, not quite a sheaf. What makes it a sheaf is the observation that when the information from this side and the information from this side matches up, then in fact I'm looking at some kind of coherent world state like this. I can make an implication about something going on in the union. So the mental picture is start out with data over the open sets, check for consistency on the overlaps. If the overlap information is consistent, then in fact you can sew it together. Of course, this works with continuous functions instead of pictures and many other things that you can imagine. In fact, surprisingly, or perhaps not, pretty much any kind of data integration question that involves pulling multiple sources of information together basically amounts to the specification of a sheaf. And where it fails to be the specification of a sheaf, it's usually because there's something wrong with the data. As in there's duplicates where there shouldn't be, there's ambiguities where you simply can't resolve them in some fashion. Good example of this sort of thing is that cameras, if those are, say, for instance, IDs and I'm merging across databases, if I have duplicate IDs that actually mean different data entries, I can't make this implication, and that's a problem. This actually happened to me a lot when I used to fly. The name Michael Robinson is very common, and I would get flagged on some kind of database that involved me losing my passport for long periods of time. Not cool. That was due to the failure of a particular set of databases not being achieved. Okay. So now let me specify this very, very concretely for a simplicial complex. So start out with simplicial complex over there. Remember, I can think of this thing as a preorder over here. And what I do is for each simplex, or each element of my finite topology, each point in there, I assign a vector space. And then each of these arrows are somehow some kind of vector space maps, some kind of linear maps. Okay, so that's assigning these data spaces and these linear maps. Well, every time that I have an overlap, I have an intersection, I should be able to pull back. So every time, say for instance, I have this star of this set here and the star of this guy over here, remember we're assigning data to open sets, and they intersect, well, then I should be able to pull back and build something over their union. And of course there's many more that I didn't bother to show here. The idea is that all of these various unions, of however you imagine, written for every element in your topology, that specifies all the data. Surprisingly, this is actually canonical. If I start out with this small description here, I can uniquely build the rest of the thing. That's called sheafification. I try to get that word into every talk I give because it's lots of fun to say. And the point of the matter is that uniquely defines this data structure in some fashion. And what we want to do in this talk is tell you how to compute certain invariants in the structure. Okay, now let me be, again, a little bit drilling down into the details a little bit more because we need the details. Here's my simplicial complex from before. I want to think of this as a preorder. So here it is as a preorder, listed out in various arrows. You can think of this as like an attachment diagram telling me how to attach various simplices together. That's pretty nice, okay. And what I do then is I assign data spaces to this. Here I've assigned them kind of randomly, various vector spaces. It's a sheaf of vector spaces on a simplicial complex. And what we name each one of these guys here, this is called the stalk over that simplex. And here's a place where the finite topologies matters. In the usual sheaf theory literature, this is not a stalk. This is a set of sections. If I want the stalk, I have to do some kind of limit process. Here, in finite topology's case, because I can form stars, I can just outright say they're stalks, which is very nice. Now, it's not just the spaces. There's translations I need to put in there. And I better pick the right kind of translations. If I got vector spaces, I should choose linear maps. If I got groups, I should choose homomorphisms. If I've got data from category X, I better choose morphisms from category X. Awesome. Okay, so some linear maps. Here they are. Here are a bunch of matrices that are somehow adapted to the data spaces. So if I map from R2 to R3, I better have a 2x3 matrix. Indeed I do. Want to map from R1 to R2, better have a 2x1 matrix. And indeed I do. Now, I can't assign these completely randomly. They're not completely up to me how to specify them. I specify some collection of them, and then, gosh, I better specify the rest. And they tell me how. They tell me, according to the diagram, commuting. Basically, composition of matrices following the arrows had better be path independent. And indeed, this diagram is such. So that if I follow around that blue square there in one fashion, doesn't look like a square, but I'm a topologist. So if I follow around, say, the top of the square, that's one matrix multiplication. If I follow around the bottom, that's the other. And indeed, those matrix multiplications are equal. So box checked. You can check the whole diagram if you care to. So that's what a sheaf is then. And then you can build out all of the unions if you want. Okay, cool. Now, what I can do now, these are vector spaces. I can actually pull out individual vectors and analyze them and see how they flow around the network, flow around this construction. So in particular, if I sit down at the top vertex there, and I put a 1 there, well, if I map through this restriction map, remember I'm going from a star over a small set, this is a star over a subset, so it gets even smaller, so I'm restricting my attention. If I restrict my attention, I go through this matrix, and in fact, gosh, I matrix multiply, I get that. Similarly, if I assign some data down here, pulled out an element of that three-dimensional vector space, map through this linear map, gosh, I get, hey, the same matrix. Now that's kind of nice. I was really careful with how I chose this. If you choose the data carefully enough so that no matter how you walk around the diagram, everything matches up perfectly, that's called a global section. Cool, okay. Now of course, if I got this adjective global section in there, maybe I can like break that rule. Yeah.
Just to make sure I'm understanding your example, on the previous slide, I mean, you have picked these matrices. This is not a unique choice.
Oh yeah, sure.
Right, this is...
Right, and so from an application standpoint, these are often given to you.
Okay.
So now applied comment, if these spaces here are telling me, say, cameras or what have you, these maps then are doing something like data translations between camera perspectives. They're given to you for very physical reasons. And in fact, failure of commutativity is an indication you've got the wrong transformation. Yeah.
Right, I was going to say, like, so many of them can be given, but the rest of them
right.
have to fall into line.
That's right. The whole thing snaps into shape once you've specified enough of this thing. Yeah, and actually, it's kind of fun if you just lay down one of these diagrams kind of randomly and start playing with them. You'll find sort of intuitively, some fraction of them, and suddenly everything's defined. And it really depends on the topology of the space. Kind of nifty, and fun. It's fun to make these slides because you get all this matrix multiplication going on. So, okay, so all right, so I got this global section. I specified everything perfectly, but of course it's kind of brittle. If I change that 1 up at the top to a 2 and left everything else the same, well, gosh, now I'm going to have 0, 2 here, and here I'm not going to have 0, 2, I'm going to have 0, 1, just as before. This is not a global section. This is a section that is manifestly local, specified over some portion. And way in the other corner there, I didn't specify anything at all. Okay, so it might be the case that I don't have global sections, and really a lot of what sheaf theory amounts to is finding out obstructions for certain local sections turning into global sections. And so a lot of the machinery basically boils down to finding those sorts of things. Cool. Okay, so I can find out whether or not sections are local or global or whatnot by doing this kind of computation. Okay. Now, if I have a sheaf and I have another sheaf, I can do things to them. See, here are 2 sheaves. 2 sheaves over, this one is in fact not over a simplicial complex, this is over another kind of space, no big deal. In any event, I have these
Michael,
2 sheaves.
Can I ask a question?
Yeah.
Sorry.
No, go ahead.
But going back to the previous, so by the 1 and the 2, do you mean like the scalar 1 and scalar 2, or
Where? Here?
Just at the very top?
Yeah, this is a scalar.
Scalar 2.
So what's this is a 1 by 1 matrix. So
Okay,
this
okay.
1 by 1 matrix times this 2 by 1 matrix.
Right.
That's right.
So you're saying that that 1 by 1 matrix
Mhm.
represents something that is not a global.
Well, that 1 by the collection, the 1 by 1 matrix here,
Yes.
and all of the, and in particular this guy right here,
yeah.
that ensemble of data that I've chosen is somehow not self-consistent.
Yeah.
It somehow doesn't jive with the sheaf structure that I specified.
Yeah.
Yeah. Okay. So importantly, if I have then a section over on this sheaf or a section over on that sheaf, are they related? Well, probably not a priori. But if I have some way to translate between sheaves, then I can do that. And, well, the way to do that is to say, well, what I need to have is some way to translate between the data over these various sheaves. I need some maps. This thing is called a sheaf morphism, i.e. a morphism in the category of sheaves, if you want to get fancy about it. I won't be fancy. Basically, a whole bunch of linear maps that translate this vector space into that one, that vector space into that one, in such a way that, of course, what's coming next? Homological algebra is giving a talk, therefore, diagram has to commute. Okay, and of course, again, like the comment that we had just a moment ago about, I specify some portion of this and the rest of it snaps into shape. The same is true with specifying sheaf morphisms. Specify some part of it, snaps into shape. Yeah?
Sheaf Sudoku.
Sheaf Sudoku. That's essentially what I was doing. All right, excellent. I got to market that. Okay, so now I've got all this data. Lots of linear spaces, all sorts of maps. Gosh, everything is kind of complicated. We need some ways to tame the nonsense. We need some algebra, some homological algebra in particular. And homological algebra is just awesome. And it's built off of linear algebra. So, like, if you take linear algebra, you realize that one of the key theorems there is this dimension theorem that says if I have a single linear map between 2 vector spaces, I really ought to think of this as ripping apart the spaces A and B into 4 fundamental spaces that are preserved by this map. The kernel, which gets mapped to 0, the co-image, which doesn't, and on this side, the image, which is what stuff got mapped to, and the co-image, the stuff that was left over. Okay, pretty handy. You can find this decomposition using the singular value decomposition if you care to, and that's all very well and good, and that's what linear algebra largely is about, is computing these things. Cool. Well, if I take a bunch of linear maps, because I've got all these linear maps and they compose and do all sorts of crazy things, I should do the same kind of thing. The analog of the dimension theorem is an exact sequence. One in which the image of the first map, F over there, matches up exactly with the kernel in the next one. The image gets taken and squashed down. Wow, that's kind of neat. And you can see it sort of pictorially what's going on. I take the whole image of F, it's here, and it becomes the kernel of the next map. And they nest together like this very nicely, and you get the same kind of decompositions floating around. So that's what an exact sequence is. And exact sequences are generally awesome. Here's an example. They exist. So if I take, for instance, this map here, and I say, what is the image of this map? Well, it turns out it's exactly the kernel of this map. And similarly for all the other consecutive pairs. So the image of this map is exactly the kernel of that map, the image of that map, etc. So exact sequences are pretty neat. Again, you can do exact sequence Sudoku, I guess, as I did here. And once you've got these things floating around, you find out that they're rather handy. See, a lot of properties of linear maps that you might care about, like are they injective or whatnot, can be encoded diagrammatically by asserting that these diagrams are exact. See, if I assert map F there is, that's a linear map, and I assert that sequence is an exact sequence, then what does it say? It says that the kernel of F is equal to the image of this map. Well, that's a map that takes 0 to 0. The kernel of this map is trivial. Ah, that's an injective map. Over here, I say the image of F is what is in the kernel here. The kernel here is everything, so the image of F is everything, i.e. a surjective map. Put those two pieces together, you get F being an isomorphism if I put zeros on either side. If you extend one step further, you get a vector space quotient. Exact sequences are really handy for encoding these properties diagrammatically. Now, exactness is really, really special. Most sequences that you write down aren't exact, and most sequences that crop up in real life, so to speak, are not. What really tends to happen is that the kernel tends to subsume the image, but there tends to be a little left over. That's called a chain complex when that occurs. So, easy way to identify a chain complex is if I compare two maps, one after the other, compose two maps, one after the other, I get 0. That says that the image is a subspace of the kernel. A little more general, that's called a chain complex. Exact sequences, of course, chain complexes, but not necessarily the other way around. And there's something called homology that computes the difference or the distance between an exact sequence and a chain complex. So how does that work? Well, basically you do the only thing that's really reasonable. You take a chain complex like this big one here, and it can go on for forever in either direction if you care, or not. And what you do is you ask for what is the difference between the kernel and the image, i.e. what is the quotient? The image is a subspace of the kernel, so I can take this vector space quotient, compute that sort of thing. If I've got an exact sequence, the kernel is actually equal to the image, so I quotiented everything in the kernel in that case, so the homology is trivial in an exact sequence, and that's if and only if the image. So homology is a way to measure when chain complexes are exact, and if they're not, how far away they are from being exact. Now, why would I care about doing this sort of thing, especially since I'm saying about sheaves and whatnot? This is all algebra. How do I pull them together? So let me do that now. Well, the way I'm going to want to do that is I'm going to want to actually think about exact sequences of sheaves. So, well, gosh, I'm going to just generalize. I've got a bunch of sheaves, 3 of them here, and the red guys are the sheaf morphisms, the collections of maps going from one sheaf to the next. They're linear maps, the whole diagram commutes. I'm going to say this is an exact sequence when it's exact along the stalks. So if I grab out a sequence of stalks, compose any 2 of the sheaf morphism component maps in red that I can compose directly, I'll call that exact. So I'm going to want to link up exact sequence of sheaves with exact sequences in general and compute some homology. Fit that all. Well, that seems like that's a good direction to go. Let's see where we go with that. So what we've thus far been thinking about primarily as sheaves over simplicial complexes, cellular sheaves. Now, you can think about global sections, coming back to that, as some linear algebraic thing. Say I've got over here a sheaf over this very simple topological space, one that's got 2 vertices and 1 edge. Well, the data specified in the sheaf is telling me a vector space over each of the vertices, and data over the edge, and then some restriction maps, which I've written out very generally there, but you can think of them as being actual matrices like we were before. The condition that a section of this thing is a global section is the data over V2, here it is, S over V2, is equal to the data over V1, S over V1, precisely when I push them through the restriction maps, I get equal. Process that in a moment. Now, as you probably learned very early on algebraically, equations kind of are bad. We don't like equations. We like equations of things equal to 0. Things equal to 0 are much easier to work with. So what I can do is I can grab this term and shove it over to the other side, or grab that term and shove it over to the other side. Well, that gives me one or the other of these equal to 0 equations. All 3 of these are linear equations, of course, but these involve computing some kind of kernel of some fashion. How do I write that down as a matrix then? Well, let's take this guy in the middle. Could have alternatively taken the other one, didn't matter. Factor out the restriction maps. Now I have a matrix multiplication. So what this says is finding global sections of a sheaf of vector spaces basically amounts to finding a kernel. Well, how does that work in practice? Well, here's a sheaf. This sheaf actually represents a 3-element queue and the time history of that as you progress. So, for instance, if I have 119 in the queue, in the earlier instance, perhaps I just had 19, and in the later instance, I've only had 11, or perhaps the other way. These restriction maps are projections, and you can see what's going on, and it's sort of shifting along. Okay, in any event, it's a sheaf, and I can ask for its global sections. Okay, so let's grab that little segment that we were looking at there, take a look at the restriction maps, I've color-coded them there, and I've built that matrix I was just showing in the previous screen in general now specifically. What am I doing? Well, I'm taking a look at this vertex, this edge, this vertex. That's the red and blue matrix, and that's right here. That's matching up the data coming from the leftmost vertex. This is the data from the middle vertex, bringing them together. Notice I had to pick a minus sign somewhere. It didn't really matter where I picked it, but I picked it there, say. And similarly, I'm looking at this particular edge, taking the data from the left and from the right, pulling them together again. And then here's the data specified over the entire thing. If all of that data, what is this data? This is the data specified over each of the vertices. If I mapped that data correctly, if it is all consistent and therefore forms a global section, by the previous reasoning, this should be in the kernel of this matrix, and in fact, look at that, it is. Cool. So what this says is, if I want to write down the global sections, I could think of them as being, well, this ensemble of data, but the algebraic way to think about it, the right way to think about it, is the kernel of the matrix. And this matrix is built up by block building a whole bunch of restriction maps. Well, if I do this and I generalize up vastly in dimension, so not just vertices and edges, but then edges and faces and whatnot, I can build a chain complex. And I want to show you how that works. So the goal that we're going to go after is we're going to get a chain complex associating the sheaf over the space. And what that chain complex then will allow me to do is compute the homology. In the 0th level, the 0th dimension, it will be just the kernel. The image will be 0. And therefore, that will find the global sections. That's the plan. All right, and we usually call this cohomology because we end up going up in dimension, as opposed to before we were going down in dimension. Don't let that bother you. It's really basically a semantic difference. Okay, so what are we going to do? Well, what we're going to do, notice back here, this is all the data over vertices. So I'm going to glue together all the data from the 0 simplices and put that into one of my vector spaces, my C0 hat, or C0 check space. And that's going to specify all the data on the vertices. We do the same thing for the edges, and the same thing for all the other faces. If you haven't seen it before, this is the direct sum operator. It basically builds vector spaces by concatenating the basics. So this is saying take all the data in all the various vector spaces, form one big honking vector space, and that's what we're going to go with. Okay, cool. Now that is only part of the problem. The other part of the problem is I got to do all the restriction maps, mapping all the data from various places. So how do I do that? Well, I said I'd block assemble all the restriction maps. So, for instance, what I do is I grab associated to two simplices in my complex, grab out that restriction map, find where the row and column corresponding to those simplices are in the matrix based on that direct sum, and drop it in there. And of course, this being the ugly little secret of homological algebra, I got to choose the signs appropriately. Beware. Choose the signs appropriately. Or just work over a field with two elements and don't worry about it. That's always the cheating way out of this. Just say, all my coefficients are binary numbers anyway, so I don't care. Don't let that bother. Okay, so once I've done that, I've built up this chain complex. It's a little bit of a theorem to show that, in fact, this thing is a chain complex. And it matters, that's where those signs come in, is to show that, in fact, stuff gets canceled out when I go from one to the next. Do that, that gives you a cellular sheaf cohomology. Okay, and the cool thing about cellular sheaf cohomology is on the 0th level, built up all the data on the vertices, mapping to the edges and checking consistency. That's actually the space of global sections. So that generalization, box checked. But now there's a lot of other spaces to tell you about things like non-collapsible data, data loops in your space in some fashion, about interrelations of the data, and various kinds of abstractions. Now, what's kind of neat about this thing, too, is it's a function. If I take two sheaf morphisms, compute their various cohomologies, it yields some kind of map between the resulting cohomology spaces. Well, that's kind of nifty. I wonder what we can do with that. Well, all right, that was cellular sheaf cohomology, where I started with simplicial complex. What do I do if I just have a random finite topological space, an Alexandrov space? Perhaps an Alexandrov space built off a preorder, like I've been thinking. Well, that construction is going to work. Why? Because I organize things by dimension. I don't know what dimension means for a random preorder. So I got to do something different. See, one of the things that's going on, this is still the complex that we were looking at a little while ago. If I organize my data like so, and I focus in on one star over one particular simplex, then I get an exact sequence like this. And in particular, the reason why I did not get homology in this case is because I'm focusing my attention on a single point and not asking for any consistency checks, cross-consistency checks. If I focus my attention on a vertex and the star over that vertex, what did I say about the sheaf diagram? It's commutative. So that means if I go around this way or around this way, I better get the same answer, always. Global section or not. That makes this diagram, in fact, commutative. Because what happens? Well, makes this diagram exact. Why? Because I went from the data over there to the edge, so from the edge data to the, vertex data, edge data, face data, and if I went one way or the other way around this diagram, went around one way or the other way, I came in with different signs. And since it's a commutative diagram, they cancel out exactly, perfectly cancel out. And so really the only time I get non-exactness, i.e. interesting homology associated to this complex we just built, is when I'm not looking at the star over a simplex. I'm looking at the union, i.e. global sections. I want to find the whole thing, not just over one point. But if I look just at one point, I end up with an exact sequence every time. This is actually the way in to generalize, in fact. Because what you do is you say, take that exact sequence. Well, I don't know dimension anymore. I've got a preorder. There's no zero-dimensional elements in my preorder. They're just all sort of lumped together. So I don't have any choice but to take that whole diagram, all of those spaces, all of those vector spaces, stratified by dimension, and glom them into one big honking massive vector space over every possible open set. Now, normally, if I have an uncountable number of topological spaces, this is a big bad vector space, probably a function space of some fashion, and people spend a lot of time messing with this thing. In this case here, because we're in finite spaces, that's still a finite dimensional vector space. I can still compute with that. Awesome. So that's the real benefit of these finite dimensional vector spaces and finite dimensional finite spaces in general, is that this thing is now a finite dimensional vector space. It's disorganized hodgepodge of all of the various other data. So it is. This is all I can do. So I got to do something else to make this space a little more workable. I got to do something about it to clean it up and make it something that I can talk about. And that's what this Godement resolution does for me. Thus far, we've had something that goes under the name of the check resolution, which really assumes that I know something about dimension. Here I don't know anything about dimension. All right, so what do I do? Well, this is what I got thus far. I've got a space that says, well, each of the various stalks in my sheaf, they represent the data over various points. Okay, now there's a lot of other junk in there too. There's a lot of stuff that is not global sections. If I just take a look at global sections on that side, most of them, well, all of them map to sections of this thing, but this thing's got a lot more junk in it. It's a sheaf. All the restriction maps here are projections. And here's one of the interesting things. Remember I said it's the direct sum of all the data over all the stalks everywhere. What happens if I went from a big space, then, big set, to a smaller set? Well, I just forget the stuff that wasn't in that set. So in fact, all these restriction maps are projections. This turns out to be really crucial when we start computing with these things. So this is a sheaf. It's a very constrained sheaf. It's way too big. We want something smaller. We want really to understand what's the difference between this thing and the global sections. So what I do is I just say, well, gosh, let me make an exact sequence of sheaf morphisms. How do I do that? Remember, what does it mean for a sheaf morphism, sequence of sheaf morphisms to be exact? This is exact on each stalk. So walk along the component maps, compose them as I go. If I walk along the component maps, composing as I go, and I've only got one component map to begin with, and I want to make an exact sequence, well, gosh, I just quotient along and throw away everything that wasn't good as I go. So I can form this co-kernel, essentially, this quotient. That's an exact sequence. It's basically all the stuff in C0 that wasn't section. All the stuff I didn't want. It too is a sheaf, surprisingly. Now, the problem is that this is a sheaf that I don't know anything about. Like, I don't know any more about this guy than I did about the sections of the original sheaf. That's kind of unhelpful. I kind of know what the structure of this thing is. I know it's bad, but I kind of know what it is. But I don't know anything about this, and I don't really know anything about the other side. So I'm going to do something else to here. This thing's a sheaf, right? That's what I said. So let me do the standard mathematician trick and say that, well, gosh, I don't know what to do, but I know what to do with this thing because I know what it is. So I'm going to make that snake swallow its tail. I'm going to take that thing and say it's a sheaf. I'm going to just do the same stuff all over again. All right, sheaf, shove it into a C0 thing of that. Basically take all the various stalks of this thing, whatever they are, glom them together, make a new sheaf. I'll call that thing C1. Well, that seems like a stupid trick, but hey, it works. And well, I don't know anything about this thing, but I know that this map here should be made injective. So I make another Z space. Okay, I don't know anything about that, but well, let's do it again and keep going. And I just keep going until I run out of energy or something, or data or whatever. So this thing is an exact sequence of sheaves. Oh gosh, that was kind of obnoxious, but so it is. That is the Godement resolution. And in fact, that works exactly, as I said, in finite spaces. It works exactly that way in any topological space, although each of these things is typically some uncountably infinite dimensional function space that you don't want to deal with, unless you know something else about it. Like there's some wonderful theorems about compact perturbations that allow you to say something about it. That's not true in general, but in this case it works great. Okay, so theorem, surprising theorem. Not so easy to prove theorem, in fact, that this exact sequence that we just computed, the homology of that thing, if I put in, instead of U's, I put in the whole space, is in fact exactly the sheaf cohomology we computed. And this is the link up. Because the whole point that spawned this talk was Professor Casey asking, this cellular sheaf cohomology that you talked about in August is all wonderful, but how does it relate to the general machine? This is the general machine. And this theorem says that, well, if I've got a simplicial complex, then this is all going to compute the same thing exactly. Of course, if I don't have a simplicial complex, I can't compute the other ones, so who the heck cares what it computes? So the point is I've removed that restriction as a simplicial complex. Kind of beautiful, kind of wonderful, even though it's sort of a dastardly machine. Well, how does this theorem get proven? Because it seems unreasonable that I should be able to prove a theorem like this. My thesis advisor says in his book on tabular theory, this theorem is a heck of a lot harder to prove than it has any right to be. And that's true. It actually is kind of intricate. Let me just give you the flavor of how this works. What you try to do is you try to build a map between these two exact sequences of sheaves, these two resolutions of this sheaf. Okay? And that map has got to be something that's very nice. That map has to preserve homology. It is, in fact, has to be a chain homotopy, as it's called. I won't prove that it's a chain homotopy. That's the hard part. I'll show you just how to build the map. And that's the easy part. So the way you build the map is, well, on the first level, I can build this arrow right here. That's equal sign. I don't have to do any work there. Anyone can build that. The second one, well, I ask, what is the data here versus here? This is, remember, the space of all the stalks over the vertices. This is the stalks over every possible open set, or every possible star open set. Anyway, point to the matter is, everything over here specifies everything over here because, well, if I take all the stalks over the vertices, which lie here, I'm going to go row into column, but this is the matrix described in this map, that's the only data I know, is the data over the stalks over the vertices. Well, that maps into wherever I've got the vertices over here. Let me just assume, without loss of generality, happens first. There's a big identity matrix there. Now, how do I get from the data over the vertices to the data over the edges? Restriction maps. So I drop in all the relevant restriction maps here. How do I get to the higher dimensional cells? More restriction maps. And I just build out this matrix with all the restriction maps I can imagine. Again, if I'm dealing with infinite dimensional spaces, well, this is going to be a pretty awful thing to write down. Again, I'm in finite dimensional spaces, finite topological spaces, no problem, I can write down this. Okay, got the first map done. Now what do I do after that? Because I don't even really know what this thing is. I know what this is, but I don't really know what that is. What do I do? I mean, I constructed this by swallowing its tail in some awful way. I've got to make that happen. Well, it turns out that these sheaves are all very special. They're sheaves that are called injective And I'll tell you what that means in a little bit. Basically what injective means is that I can, whenever I've got a structure like this map, that map going on, then I can automatically fill in another map right there in red. Okay, well that's kind of interesting. What does that do for me? Oh wait, I can compose this map, that map to get a map from here to here. And that's exactly what I do. Same kind of nonsense where I just keep repeating the process. So now that's great, and then I say, well, how do I make this map? Repeat the process, do the same thing. Form this map because this guy's injective, because it's basically the same kind of sheaf as that one is, and just build out the whole thing. Well, that's cool, that builds up this map. So now I have to tell you about injectivity. So injective means precisely that. When I have a diagram that looks like this, I can fill in that map right there. Okay, why does that work for sheaves? Why does that work in general? Well, it works in general for vector spaces. If these are vector spaces, then I can always do this. If basically by just projecting in the right way. If I'm talking about sheaves, the diagram maybe looks like this, and I can't always do this. But if I've got the sheaf in which the restriction maps are projections, then they typically look either like V maps to V, trivial projection, or V maps to 0 for some subspace, collapsing out some portion. Well, in that case, well, I have to form this component map of the sheaf morphism and this component map of the sheaf morphism. This is like part of the diagram. This one, look, that's a 0 map. I don't have to work for that. This one, well, now this is just all on the level of vector spaces, and I said you can figure that out. It's an easy linear algebra exercise that I won't do now. So you build that map, box checked, and then the only thing you gotta ask is, did I make a commutative diagram? Because that's the thing that goes wrong in general. Well, if you follow around this blue and black box, well, that was already there, so that's commutative. Same blue and black box over there. So really the things I gotta check are the two red, black triangles. Okay, this one's with the 0 back there. There's nothing to check. This front here, we made it happen that way. So then there's one more, the blue and red box, blue and red square. And that's where the fact that this maps to 0 is good. If this were 0V the other way, you'd be out of luck. Doesn't work. It's not an injective sheaf. Cool. So the fact that we chose these C0s as being sheaves of all the component data projecting down was essential to making this argument. And that says then that I can build those maps and then everything else works. And of course then you're left with the hard part of the theorem proving that this thing actually induced the right maps on homology. And it does. So let me end with an example. Because this is actually the real whole point of this, is I wanted to say, you can actually compute with the Godement resolution. So if you just take a cellular space, this is a sheaf over a simplicial complex where I have a vertex, edge. Well, that's the data on it, and you can write down the various cellular cochain spaces. So this is the data over all the vertices. There's an R and an R. There they are, 2 R's. Data over the edge. There's R2. Build up my map by glomming together the various restriction maps. Here they are, the first one and the second one. There they both are. Remember, I had to put in a minus sign to make everything work. Okay, compute the kernel of this matrix. I bet you can see that the kernel of this matrix is given by what? 1, 1, right? And that's it. Aha, 1 dimension. Now, what about the quotient of R2 by the image of this matrix? This image of this matrix is 1 dimensional, so R2 quotient, 1 dimensional thing, that's also R. So H0 is R, H1 is R, and everything else is 0 because there's like nothing else there. That's the easy case. This is the case that I advocated for strenuously for applications. But now let's do the Godement resolution. It's a little bigger, but not undoable. See, here's the C0 space, glomming together all the various stalks. This is the stalk over this vertex. This is the stalk over this edge. Over the edge, I only have the edge to worry about higher dimensional. Remember, I'm working with stars. Similarly, that vertex, its stalk went here. There's the edge. And then what are the maps? Well, the maps are all these glomming together of the restriction maps in various ways. There they are. And the injection of each of these things, making them making my exact sequence, just basically translates the data along, taking the data from this edge right here through this 1, and then if I were to go from this 1 to this edge, how would I have to go? I'd have to restrict through 1, 0. Aha, there it is. Okay, so these component sheaf morphism component maps get mapped along. I didn't write in the maps for the top row because they're the same as the bottom. That made me C0. Then I need to make the Z's. I need to quotient them. I've made them gray here because they're not actually part of the Godement resolution, but that's fine. How do I quotient them? Well, I say, what's the quotient between R2 plus R, i.e. R3, quotient with this map? This is a map that has a one-dimensional image, two-dimensional. What's R2? Quotient, the image of this identity map, which is, of course, R2 quotient R2, that's 0. And, of course, the top is the same. And, of course, this is the canonical projection map. Cool. Okay, and then mapping from Z1 into then the space of all the stalks. Well, this is actually pretty easy, because like this is R2, and what's the stalk over the edge? Oh, that's 0, so it's R2 plus 0, R2 plus 0, and that's 0. And, of course, everything else is 0. So let's go to my resolution. I think I should write down the whole thing. But no, I'm not done, because I need to give you the cohomology of this thing. All right, so how do we do that? Well, I take a look at the thing over the whole space. Just basically asking for it to be computed over the whole space. These are, in fact, the vector spaces in question. Basically glomming together, finding all of the data that are consistent with these diagrams. This actually involves a little bit of work. Since I've got 2 minutes left, I'm not going to show out how to do that computation, but there you are. Suffice it to say, I did it. I didn't stress very hard making it happen. Okay, when I do that, then I end up then with this particular sequence, this chain complex. There's the map M, which again comes about by taking these component maps and sticking them together. This component map here ended up in this block right here. This similar component map on the top ended up down below here, and then sort of flipped around a little bit. In any event, that is the map that defines everything that's happening in the cohomology of this chain complex. It's rank 3, it's easy enough to compute because this row and that row are the same, so rank 3. That means the homology of this thing at level 0, so the 0th homology is the kernel of this matrix. Hey, this is it's a something by 4 matrix with rank 3, so its kernel is dimension 1, indeed it is. And R4 quotient the dimension of the image being dimension 3, that's an R. Hey, these are exactly the same values that we can do before. Box check, this isomorphism theorem is in fact true. So in fact, in conclusion, essentially what this is saying is it's actually possible to compute the Godement resolution when you're dealing with finite spaces. It's exactly the same thing as the Sheaf cohomology for a cellular space, as I suggested. Now, you probably don't want to compute the cohomology using the Godement resolution unless you're forced to. I'm giving a talk on how to do it. But it can be done. And with that, I will say, oops, thank you.
Thank you, Peter. Questions? Observations?
Yeah. Go ahead.
The resolution, the Godement resolution over infinite dimensional
absolutely.
spaces, choice is involved.
Absolutely.
Right.
Yes.
I mean, is it?
Well, because then essentially what you want to do, the reason why the choice is involved is in specify, you don't have to specify this whole thing over, and this is a point I glossed over, you don't have to specify it over the entire topology, but over a base for the topology. So the choice that then amounts to is you can simplify things very easily by choosing a more useful base for that topology. Choose a stupid base, you're going to be doing a lot more computation. Other questions? Yeah.
So, if you don't necessarily want to use the Godement resolution to compute the Sheaf cohomology
That's
because
right.
it's too complicated,
Mhm.
in what sense is this a tool that's useful to you? Or,
Remember I said this was not applied talk.
okay, okay.
This was merely the question, if you can do it, what the heck does it look like?
Got it, okay.
Really? And I strenuously argue that you should never compute this thing directly unless you have to. I would say always compute the cellular or simplicial sheaf cohomology,
Yeah, okay.
because it's much, much better. And in fact, there are actually some recent results by a bunch of friends of mine that say in many cases you can reduce that computation down tremendously by doing appropriate algebraic simplifications. And in fact, if history is any guide over the past 10 years, on the level of just plain old homology, not Sheaf cohomology, the key computational thing that helps in making these things practical is the reductions of these by doing algebraic reductions to simplify the computation in the first place, so that you end up with a much smaller chain complex.
Translation, these make good exercises for students who are doing this.
These make terrifying things for students. They were a lot of fun for me to do, but potentially terrifying. So I'll end then if you're interested in all these big scary diagrams, next semester I'm teaching a computational algebraic topology class. So much more diagrams will ensue and lots more fun. So if you're interested, please take it. Thank you.
I think we should thank the speaker again for. Well, thank you. Yeah, let the computer cooperate.